I shall now find a formula for the period of a pendulum. So let's say that's my little red ball, and it's suspended from the ceiling by a bit of string, and let's say this is the vertical line. Okay, now right, so when this is displaced to one side, the force of gravity will be acting on the ball with a force of mg, its weight, and this would cause the ball to want to swing back to its rest position, which is here. Now I'm going to think about the displacement. I'm going to think about the displacement in this direction as x, so that would be the positive x direction, that's the negative x direction, and that's the zero displacement position, that's the rest position. Okay, now in order to obtain an equation for the period and a formula for the period, I need to make use of the simple harmonic equation and the formula relating period to omega. Right, so the first thing I need to do is to like what I did for the spring, to consider the forces and to try and obtain an expression for or a formula for omega squared in terms of the physical quantities here. So let's have a look at what are the physical quantities that are obvious. There is the mass, there's the force mg, and there's also the length of the string. I'll call that L. Okay, so as this swings to and fro, the reason why it would swing to and fro, why it would swing back to its rest position, is because of the weight pulling it down. But let's analyze this weight a bit more. I think I've explained in an earlier session that if I resolve this weight into two components, one along the string and one perpendicular to it, okay, I would actually find that this component along the string, it does not affect the motion directly because it is balanced by the tension in the spring, and it is this perpendicular component that actually pulls the ball back to its rest position. And this component, let's see what the value of this component is. It depends on this angle theta, which is the same as this angle. Now we can see that this component must be mg times sine theta if we draw this right angled triangle here, this right angled triangle there. So therefore I have an expression for the force. The force is equal to, this force here is equal to mg sine theta. Okay, now this force here, according to Newton's second law, it should also be equal to mass times acceleration, right? It should be equal to mass times acceleration. But there is a catch here, because I want to consider the acceleration along the x direction, whereas the force is not exactly along the horizontal direction. It's slightly slanted. Okay, it's quite horizontal if the angle is small, but nevertheless it's at a slight angle. So what this means is that this is only if I'm thinking about acceleration along the x direction, Yeah, I'm thinking about acceleration along the x direction, where the ball would accelerate back towards the rest position. Right, I want to think about the horizontal component of the acceleration. Since the force is slightly slanted, this relation would only be approximate. Right, these are only approximately equal. But it is good enough for small angles, because we'll usually be just dealing with small angles for a pendulum. So, or not really, but for what we are going to, the formula that I'm going to derive, it will usually we can normally only use it for small angle oscillation. Okay, so let's carry on. I would now need to express this in terms of x. Right, eventually I want an expression that contains a and x so that I can read off omega squared from the equation. Now, x here, x would be, let's see, x would be the distance from the rest position to the ball. So it would be this distance here, right angle. So that's my x. That's my x. Now this distance is related to the angle and to L by sine theta. So I have my approximate expression. On the one side it is A, on the other side is mg, and sine theta is x divided by L. Remember why this is approximate is because the force given by this expression, this one, is not exactly the same direction as the acceleration and displacement direction. Okay, so that's why it's only approximate. Now that we have this expression, okay, we need to do one more thing. Actually, we need to see that the force here is actually in the negative direction of x. So that's why I need that. So I would need a minus sign here actually, and here. Okay, and from this equation, I'm almost there now. I can cancel the m. I can divide both sides by m. And once I've done that, you can see that I have a already here and x there. So I'm just going to rewrite this into a more direct form. So g over L, I'm going to write x separately. So now I can compare the two directly. Omega squared is just g over L. So therefore, omega squared is equal to g over L by comparing the two, and omega is equal to square roots of g over L. Now if I substitute it into this expression, I would be able to find a formula for t. So 2 pi divided by omega. That would be, so this would become upside down, L over G. Square root of L over G. So there we are. Now we can, if you look at this formula, you see that L is on top of this fraction. And what this means is that if L is longer, if the length of the pendulum is bigger, this formula suggests that the period would also be longer. It would take longer for the pendulum to swing to and fro once. This is something we can easily check. Just take a bit of string, tie a little ball to it, and swing it once, and then use a longer string, tie to the same ball, and allow it to swing once. And you'll find that the longer string would always give a smaller period. And the other thing that is interesting about this formula is that the mass of the ball doesn't appear. See, it has already been cancelled out here. Okay, and this is unlike the case for the spring, in which the mass appears in the formula for the period. So in this case for the pendulum, the mass does not appear. Now, what is also of interest here is that the amplitude right, the amplitude of the motion, the maximum displacement, does not appear in the formula for the period here either. It also did not appear in the formula for the period in the spring. So what this means is that the simple harmonic motion, right, the period does not depend on the amplitude. So this is a very important result for simple harmonic motion, meaning that if I move this ball a bit further out and let go, as it swings, it will have the same period. If I move it, displace it just a little bit and let go, and it swings to and fro a little bit, it would also take the same time for one cycle. And likewise for the case of the spring. So that's what this means. The period does not depend on the amplitude. Now, and while we are here, there is one thing that I should emphasize. In the case of the pendulum, however, this is actually strictly true only when the angle is quite small. Because if you remember, we made this approximation here. Okay, we had to make an approximation here because the direction of force is not exactly horizontal. But I said that it is quite accurate if the angle is small, right? Then this force will be quite horizontal. But for bigger angle, this force will be clearly slanted, and this equation will be less accurate. And in fact, it would not be exactly a simple harmonic equation, unlike the case of the spring, which has this form exactly as long as Hooke's law is true. So if the angle gets too big, actually, for a pendulum, the temperature will increase with amplitude. It will depend on A. But it will not depend on A for small amplitudes, maybe a few degrees. So if you're talking about the difference between 1 degree and 2 degrees, or maybe even 5 degrees, then the amplitude will be more or less the same.